Okay, welcome to this short series where we'll be exploring new logics. In particular, in this one, we'll be exploring Lisbon logic. So we'll start from the beginning. A lot of you might have heard of Hoare logic, and Lisbon logic is just a slightly different take. So we'll start with Hoare logic and we'll see where the difference lies essentially. So let's write that down. So we're going to start with Hoare logic. Okay, and in Hoare logic, what we're basically trying to do is we're trying to specify and prove properties about our programs, and in particular, those properties have the form of Hoare triples. So let's write such a triple down. So we are going to have a precondition, which we're going to denote with P, and it basically restricts the inputs or the starting states of our program. Right? We're only considering programs that satisfy a certain precondition P. Then we're going to have our actual program, which we're going to denote with C for command. And then we have a postcondition, which is an assertion about... It's an assertion about what properties the final state or the output of a program should satisfy. Okay, and so this is a Hoare triple, and we can be a bit more formal than this, right? We can say exactly what this Hoare triple means. One thing to be more specific about is that in Hoare logic, in partial Hoare logic, we only require that the postcondition Q is satisfied if the program terminates. So if the program doesn't terminate, then it's fine, right? It doesn't take termination into consideration at all. Okay, so if we were to write the semantics of Hoare triples a bit more formally, we could say, so this V double dash here means the semantics of, so the meaning of this Hoare triple. And the meaning is as follows. So for every state, and we're going to call this state sigma, in some set of all possible states that our programming language allows, right? So that's the big sigma. So for all states in sigma that in particular satisfy the precondition. So for satisfiability, we're going to use, again, we're just going to use V double dash for now. But this is what this means. So if our state satisfies the precondition, then, so we're going to do an implication. And if it terminates, that's important. So for termination, we're just going to say, if you know big step operational semantics, if we have a derivation of a program in big step semantics, then it necessarily terminates, because if it doesn't terminate, then we can't produce such a derivation. So we're going to have our sigma and our command, and we're going to just do a down arrow for the evaluation of our program, and it's going to evaluate to some sigma prime. So if it satisfies the precondition and it evaluates to some state sigma prime, then, right, and you can read this implies here as an and, because it's just a different form. For now, we're gonna leave it as an implication, because it's equivalent when we have an implication to the right. So when that's the case, we have to have this property that the resulting state satisfies Q, our postcondition. So this is essentially the meaning. Okay, so that's our meaning of a Hoare triple. So I'm going to put that here. Now you might think, well, it's a bit like, it's not very satisfying, is it, right? If a program doesn't terminate, then, you know, how useful is the program, right? Sure, our program's correct if it terminates, but, like, let's say it doesn't terminate, or it only sometimes terminates. Not great. Like, a very simple example, if we have any triple PCQ, if you write a simple program just do nothing, right? While true, do nothing. This program trivially satisfies any Hoare triple. So it's not great, right? I mean, we can basically prove any property about a program as long as the program doesn't terminate. So we want something stronger. And that's where total Hoare logic comes in. Total Hoare logic. And for now, we're just dealing with deterministic programs, right? So programs that their output only depends on their input. So let's make this stronger. And we're gonna, this is called total Hoare logic. And let's give it something to differentiate with. Let's give it these bars here. Now, for all states that satisfy the precondition, now we're going to mandate that there exists I should have kept the implication there. So now we're going to mandate that there exists, given some initial state, if we execute the program C, we will end up in some state sigma prime. There must exist such a state. We're asserting that. Not only must there exist such a terminating state, right, such a terminating program, but also it must satisfy Q. Now, this is only for deterministic programs. Because I'm using an existence quantifier here. Now, in a deterministic program, that's really all you need, right? Because if you start with some state sigma, then because the program is deterministic, it will do one or two things. It will not terminate, or it will terminate. And here we're saying it must terminate and it must satisfy Q. So that's the only thing it can do. It can't not terminate. And that's total Hoare logic. Now, let's say instead that a program was non-deterministic. So given one particular input state, a program can basically, it can split into two paths, right? It can go this way, or it can go, well, the other way, I suppose. Yeah. So from a single sigma, we can end up with sigma prime, and we can end up in a different sigma prime. And that's a non-deterministic program. So not only can we end up in a different sigma prime, but what else can we do? Well, we can also just not terminate, and I will try to like a loop, if that makes sense. Yeah, so this one just keeps looping this path here. Okay, so this one never terminates really. So that's in a non-deterministic program. And now you can imagine this no longer satisfies, this definition here no longer defines total Hoare logic, because the existence of a sigma prime, let's say this one does satisfy Q, this one does not satisfy Q, and this one, well, it doesn't terminate, so there's no state at all. So this is no longer sufficient to define total Hoare logic. Let's go back to Hoare logic, in fact, regular partial Hoare logic. Now, in partial Hoare logic, we already said we don't care about the non-terminating things. That's fine. But we do care about all of these, right? All of these final states must satisfy Q. So what do? Well, we're just missing a quantifier here, right? This definition is not valid anyways, because sigma prime here is not quantified. So we're just going to add this this for all quantifier here. And that fixes our definition, basically. So it says, for any state that satisfies the precondition, if the resulting state terminates, right? If the resulting path terminates, then that resulting state must satisfy Q. So, as you can see, these definitions are they're very similar, right? All we've done is we've swapped a universal quantification for an existential quantification. And, well, we also need to do this change from an implication to a conjunction. Okay, yeah, I realized that I'm missing something. For all sigma prime. There we go. Yeah. So for all final states, if that final state is reachable from the precondition, then it must satisfy Q. Now this instead is still useful, but we call this Lisbon logic. So Lisbon logic says there exists at least one terminating trace that satisfies the postcondition. So this program here is a non-deterministic program, and it has one trace that terminates and satisfies the postcondition. So this trace here is Lisbon valid. It's not Hoare valid because we have this other trace here that doesn't satisfy the postcondition. So neither Hoare logic nor Lisbon logic are stronger than one another. They express different properties. Because again, in Hoare logic, we could have this situation. And as I showed, that satisfies any triple. But in Lisbon logic, having such a program that never terminates, it does not satisfy any triple. Okay? There must be at least one terminating trace that satisfies the postcondition. And so I think that's a brief introduction to what Lisbon logic is. It's basically this weaker version of total Hoare logic that's weaker in a different way than Hoare logic. And in deterministic programs, it coincides with total Hoare logic. But in non-deterministic programs, it has different semantics to both total Hoare logic and partial Hoare logic. And what is it used for? Well, we can use it for bug finding. We can use it for incorrectness reasoning. If Q is a bug and we give a Lisbon triple for that bug and we prove it for a given program, then we know that that bug is reachable, that there is at least one path through the program where that bug is reachable. Now, you may have also heard of incorrectness logic. Incorrectness logic uses slightly different semantics, and I might get onto what they are in another explanation. But yeah, Lisbon logic and incorrectness logic are two different approaches of reasoning about the incorrectness of programs. The difference is that Lisbon logic is very similar to Hoare logic. As you can see, we pretty much derived it from Hoare logic. Incorrectness logic, on the other hand, takes a slightly different approach. Instead of going in this forwards direction, quantifying over preconditions, it quantifies over the postcondition. So it basically flips the triple like on its head. Whereas Lisbon is just swapping the universal quantifier for an existential quantifier with regards to the traces that a program can take. In the next part, we're going to explore a validation algorithm for Lisbon triples, right? Given a program and a Lisbon triple, does that Lisbon triple hold for the program, right? We want to answer that question algorithmically. And the way we're going to do that is we're going to adapt the compositional symbolic execution theory, which I explained in another series. You can check that out. And in fact, it's probably an important prerequisite for the next part of this series. And yeah, we're gonna explore how to do that. So, see you there.